This is a torque angle meter being used to tighten cylinder head bolts. The procedure involves measuring two of the elements involved in tightening fasteners. Those elements are torque, the turning or twisting force applied to tighten the fastener, and angle, the number of degrees the fastener is turned. The torque angle meter is an electronic measuring device that provides accurate readouts of fastener torque and rotation angle. Today, we'll show how the torque angle meter is used, and perhaps more important, we'll explain why it is used. We'll also look at the increasingly important role played by engine fasteners. That's right, those crucial nuts and bolts that we probably take for granted more than any other parts we use. One of the principal goals in current automotive engineering is to achieve maximum performance from economical small displacement engines. To meet this goal, engines are being redesigned for less weight, increased power, and more efficient use of fuel. At the same time, quality and durability expectations are higher, so engines are required to last longer and be more reliable. To achieve the desired combination of power, lightweight, and durability, small engines must be designed and assembled with extreme attention to detail. The Quad 4, the 3800, and the 3300 are all new precision engines, specifically designed to incorporate these qualities. But refinements are not limited to new engines. In fact, in recent years, every engine used by Buick has had major design changes to improve performance. Increasing the power and precision of engines puts greater demands on the fasteners used to assemble them. Let's consider why. Fasteners in all automotive engines are subject to many stresses: vibration, heat expansion, internal pressures, and corrosive gases are all natural byproducts of internal combustion. Fasteners have to be able to withstand these forces and hold components together tightly enough to maintain combustion seals and prevent leakage. As torque is applied to a cylinder head bolt, the spiral shape of the bolt threads pulls the block and the head together. Eventually, the point is reached where the head of the bolt is flush with the cylinder head. When the bolt is rotated beyond this point, the head cannot advance, so the bolt actually stretches. Bolts are made from material that has a certain amount of flexibility. When they are stretched, they attempt to return to their original shape. So, the stretched bolt acts like a spring. The spring effect produces tension that helps maintain clamp load. It also helps to prevent the bolt from loosening during engine operation. The amount of clamping force produced by a tensioned bolt is measured as clamp load. As the bolt is rotated, clamp load increases, provided the yield strength of the bolt is not exceeded. The yield strength of a bolt is based on the size of the bolt and the tensile strength of the material it is made from. Tensile strength is an indication of how much the material can be stretched without breaking. The bolts used in current Buick cars are mostly metric, and they have identifying numbers embossed on the heads. These strength class numbers indicate the tensile strength of the bolt material. For example, this cylinder head bolt is marked 11.9. This puts it in a high strength class. The bolts most commonly used to hold other engine components are of class 9.8. You'll find more information on bolt sizes and strength identification marks in the Know-How Reference Manual. During engine design, strength and size factors are calculated to select bolts with the ability to produce the clamp load required to hold various components together. In deciding the correct clamp load for a specific joint, engineers consider several other factors. For example, they consider the type and strength of the materials being joined. They also consider the stresses that affect the joint in operation and whether or not a gasket is to be used. During the engine manufacturing process, computer-controlled equipment is used to ensure that critical fasteners are tensioned to produce just the right amount of clamp load for each application. It is important, therefore, that bolts are tightened with the same accuracy during service operations. As we'll examine a little later, bolts that are not tensioned enough can soon work loose. On the other hand, bolts that are over-tightened can cause thread damage and distortion of the components being joined. Our goal, then, in tightening fasteners is to produce just the right clamp load needed to prevent parts from becoming loose, no more and no less. We've seen that torque produces clamp load, and that clamp load increases as a bolt is rotated. You can see, therefore, that we ought to be able to predict how much clamp load will be produced by a given bolt at a specified torque. However, it isn't that simple. That's because a very important factor is still missing from the equation: the effect of friction. As a fastener is rotated, friction is produced between the head of the fastener and the material surface. As clamp load increases, friction also increases between the external fastener threads and the internal threads in the nut or threaded hole. This friction has a very significant effect on the amount of clamp load that is produced at a given torque value. 80 to 90% of the torque used to tighten a fastener is absorbed by friction. That means that even under ideal circumstances, when a fastener is in perfect condition, only 10 to 20% of the tightening torque produces useful clamp load. Consider what might happen in a real-life situation where bolts may not be in perfect condition. The fastener lab at General Motors did some tests to find out. They took two identical bolts, just like these, one in ideal condition with perfect threads, properly oiled and carefully broken in. The other, well, let's say it leaves something to be desired. It's dirty, there are nicks on the threads, the head is rounded, and so on. All factors that reduce clamp load. This chart shows the results obtained when the clean, well-lubricated bolt was tightened to a torque value of 88 foot-pounds. The good bolt produced 20,000 pounds of clamp load at this torque. Now, here's the result when the bolt in poor condition was tightened to the same torque of 88 foot-pounds. This time, clamp load reached less than 8,000 pounds. That gives us a clamp load variance of more than 12,000 pounds. That's a 6-ton difference. What if these two bolts were tightened this way during an actual service operation? As you know, cylinder head bolts must be tightened in a specified sequence. The sequence is designed to ensure that clamp load produced by the bolts is spread evenly over the entire surface of the joint. This is done to prevent distortion of the cylinder bores and cylinder heads. Imagine the possible consequences if a clamp load variance of 6 tons was allowed between bolts. At best, the gaskets will leak. At worst, the engine could be severely damaged. It's pretty clear that measuring torque alone just doesn't offer the accuracy needed for tightening critical fasteners like cylinder head and connecting rod bolts. So let's look at the results when the same two bolts are tightened using the torque angle method. The first step is to tighten each bolt to what is known as threshold torque. At threshold torque, the head of the bolt is flush with the surface of the material. The joint has settled down, and the parts are held snugly together. Notice that when threshold torque is reached, clamp load is still relatively low. Also, at this point, the clamp loads are still reasonably close together. The difference is still within 3,000 pounds. Now look at what happens when the two bolts are tightened to final clamp load using angle instead of torque. The difference in clamp loads produced at threshold torque remains constant. It doesn't grow worse as it did when using a torque wrench alone. The benefit of using torque angle is pretty clear. A constant clamp load difference of 3,000 pounds versus a variation of 12,000 pounds. To understand why the angle method produces more consistent results, we must consider the mechanics of threaded fastener design. As we've seen, the spiral shape of a bolt's threads serves to pull components together. The difference between the center of one thread and the center of the next is referred to as the thread pitch. When a single threaded bolt is rotated a full 360 degrees, it advances a distance of 1 thread length. Therefore, a bolt with a thread pitch of 1 millimeter advances a distance of 1 millimeter when rotated 1 revolution. Similarly, the same bolt advances a half millimeter, or half as far, when rotated 180 degrees. When turned 90 degrees, it advances a quarter millimeter, and so on. Original equipment fasteners used by General Motors conform to strict manufacturing standards. So, it can be assumed that bolts with the same size and pitch specifications advance the same distance when rotated a given number of degrees. Consistent clamp load can therefore be obtained when bolts of the same size, thread pitch, and strength class are rotated an equal number of degrees. Bear in mind also, the bolts in our test examples represented the best and worst conditions. Proper care should be taken to examine and clean bolt threads to minimize variation. If a fastener is damaged or is of a type that cannot be reused, use a replacement fastener with the correct part number for that application. If the correct part number fastener is not available, a fastener of the same size and strength or stronger may be used. The threads in the cylinder block should also be inspected and cleaned using the appropriate tap. When this is done, the torque angle method produces even better results. Gasket surfaces should also be thoroughly cleaned. Most of the engines used by Buick require that pipe sealant compound be applied to the threads of the cylinder head bolts. GM part number 1052080 is a pipe sealant compound containing Teflon lubricant. During assembly, it provides lubrication between the threads and at the head of the bolt. It also serves other purposes. A small amount of sealant is also applied to the underside of the bolt head. Fastener threads are designed so that a small amount of clearance exists between the external threads of a bolt and the internal threads of the nut or tapped hole. Without this clearance, friction is greatly increased, making it very difficult to turn the fastener. However, depending on the location of the bolt, the small spaces between threads can cause oil or water leakage. They also allow moisture to penetrate the threads and cause corrosion. Also, the clearance between threads is enough to allow a bolt to move slightly when the joint is subjected to stresses resulting from engine operation. The amount of movement may be very small, but it can create a ratcheting effect, which may be sufficient to overcome thread tension and cause the bolt to loosen slightly. Once loosening has begun, normal engine vibration speeds up the process. The primary purpose of pipe compound is to form a seal that prevents oil and moisture from penetrating the threads. But since it fills the space between threads, it also helps to prevent threads from moving against one another and working loose. To aid in production, many new original equipment bolts are pre-coated with thread sealer in a dry form. When these bolts are removed, some compound remains on the threads. However, for best results, fresh sealer should be applied. Other fasteners require the use of an adhesive thread locking compound designed specifically to prevent loosening. Like thread sealer, thread locker works by filling the spaces between threads. The difference is that thread locker is an anaerobic adhesive. The term anaerobic means it cures when removed from the presence of air. Once hardened, it forms a rigid bond and prevents the threads from moving. GM thread locking kit, part number 1052624, contains a thread primer and Loctite 271, a high-strength thread locking compound. The kit is used to retain the oil pan screws on the 2-liter L4 engine. The primer is sprayed on the cleaned screw threads and allowed to dry for 5 minutes. When the adhesive is applied, the screws must be inserted within 3 minutes. Now, let's take a look at how the torque angle meter is used to tighten cylinder head bolts. When the meter is turned on, the alarm sounds and the meter performs a self-test. When the self-test is complete, the set alarm portion of the display flashes, indicating the meter is ready for use. Pressing the Operate Set Alarm pad puts the meter in the Set Alarm mode. This pad allows the operator to adjust the meter to read in either Newton meters or pounds-feet. The specified torque value is set by pressing the Alarm Up or Alarm Down pads. When the correct torque value has been set, the meter is placed in the angle mode by pressing the Torque Angle pad. The desired angle is then set by pressing the Alarm Up and Alarm Down pads. Pressing the Operate Set Alarm pad once again puts the meter in the Operate mode. Set Alarm no longer appears in the display. Finally, the meter is returned to the torque mode by pressing the Torque Angle pad. Now functioning as an electronic torque wrench, the meter is then used to tighten the bolts to threshold torque in the required sequence. The meter's alarm sounds each time the preset torque value is reached. When all bolts have been tightened to threshold torque, the meter is placed in the angle mode. With the sensing head on number 1 bolt, the anchor clip is attached at a suitable location. This ensures the sensing head does not rotate when the bolt is turned. The angle 0 button is then pressed, and the bolt is slowly rotated the specified number of degrees. Again, the alarm sounds when the preset angle is reached. The same procedure is repeated for each bolt in the proper tightening sequence. Fastener torque and angle specifications, as well as proper tightening sequences for all engine fasteners, can be found in the chassis service manual. These specifications are often revised, so be sure to consult the appropriate model year manual for the vehicle being serviced. We've seen the torque angle method used to tension the standard metric bolts used on the 2.5-liter L4 engine. Torque angle is equally effective when used with the torque-to-yield bolts used on Buick 6-cylinder engines since the 1985 model year. Torque-to-yield bolts were introduced in the 1985 low-deck 3-liter engine. These bolts were identified by a reduced shank design. A full shank design, similar in appearance to the conventional bolt, has been used in all Buick 6-cylinder engines since the 1986 model year. Torque-to-yield bolts are designed to yield or stretch significantly when tensioned to a specific load. The bolts produce superior and consistent clamp load when the yield point is reached. Because of their special design, care must be taken when tightening torque-to-yield bolts. If the yield point is exceeded, the head gasket may fail and the engine may be damaged. The procedure for tightening torque-to-yield bolts has been updated for the 3800 and for the new 3300 engines. The revised procedure incorporates use of the torque angle meter and reduces the possibility of over-tightening the bolts. You'll find the procedure in the 1989 service manual and also in the Know-How reference manual. Granted, using the torque angle meter takes a little longer than just using a torque wrench, but with a little practice, it should become second nature. Consider the possible consequences of not tightening critical fasteners properly. I think you'll agree, the little extra time it takes to use the torque angle method is time well spent.